Okay, so this is my Module 3 Advanced Concepts presentation. My name is Nick Pippin, and today we're going to be talking about just how oxygen binds to hemoglobin and how that moves throughout our system. So to start, I just want to look at the structure of hemoglobin first. So it's a quaternary structure. It has 4 subunits, 2 alpha and 2 beta units, or alpha-beta dimers. It has four heme subgroups, and each of those subgroups contains iron on it. So we can see here 1, 2, 3, and 4, each heme group with that iron component on it. And so there's two conformations of the hemoglobin that we're going to talk about today. There's the deoxygenated version of the hemoglobin where oxygen is not bound to that heme group, and this is referred to as the T state or the taut state. In this state, it has less affinity for oxygen, less chances for oxygen to bind to that site. It's in a non-planar formation, which we'll talk about soon. And this is the predominant protein that we're going to find in our red blood cells. Then we have oxyhemoglobin. This is the oxygenated state of hemoglobin. This is considered the R state. This has a high affinity for oxygen, and this is going to be in more of a planar state, which we'll talk about here next. So, how oxygen binds to heme. So what happens is we get a movement of iron into the heme plane, and we assume that this is sort of the trigger from the T state to the R state after binding to 2 oxygen molecules. So we talk about that planar versus non-planar state. So we're looking at the deoxygenated state here, kind of connected to our iron group. We're in this non-planar state where we're just off-centered and not straight across from each other. Heme cannot bind to this quite as easily. When we do become attached now to these 2 oxygen, heme now becomes more planar and thus able to accept more oxygen, accept more oxygen in this state. And again, this is the R state as it becomes more planar. So, again, this R state that we're now in means that heme has a higher affinity for oxygen and can accept more oxygen groups. And this is going to form an octahedral iron complex. And then again, this is our oxyhemoglobin state. This conformational change makes it easier for other heme groups to bind oxygen, as we mentioned. So let's talk about the difference between the binding capacity in different locations. So binding in general is affected by both pH and torr, or the pressure of oxygen. So if we look at the lungs, our pH at the lung and in the lungs is 7.4. This is relatively high, and we have 100 torr here, which is at a relatively high pressure. So this makes a more favorable binding site, and this creates more open heme groups ready to accept oxygen. So this is a good thing. This is what allows oxygen to transfer from our lungs and into our tissues, into our capillaries. So this state very favorable to accept oxygen. As we look into the capillaries and the tissues now, relatively lower pH and a lower torr. We also have higher levels of carbon dioxide in this area, and so in our tissues, that high level of carbon dioxide makes it a more acidic environment, and this lowers that affinity for oxygen, and this causes that hemoglobin to return to its T state, or its deoxygenated state. So what this means is, when that happens, it then loses that oxygen, and that's released into our capillaries and into our tissues. So how does water play a part in this? So when carbon dioxide interacts with water in the bloodstream, it forms carbonic acid. And this is really important. So the carbonic acid will dissociate to form bicarbonate and hydrogen, as well as remove the hydroxide ions. So this results in an overall lower pH, which we saw in the last slide in the capillaries. It has a relatively lower pH. So this drop in pH will cause the release of oxygen within the capillaries, and then it'll oxygenate said capillaries. So we can see that chemical reaction here of just what this looks like. So what this does is this allows for a more regulated blood pH, and then our body will adjust to that in terms of how we remove CO2 through breathing. This relationship is obviously incredibly important because without this interaction and forming of carbonic acid, we would have less oxygen going to the tissues, and this would lead to hypoxia, which could in turn lead to cell and tissue death, which is certainly not what we want. So that is all I have. Thank you.